December 1947. Three scientists at Bell Laboratories in Murray Hill, New Jersey, are about to change the world forever. They don't know it yet, but their invention will eventually shrink room-sized computers into devices smaller than a fingernail, powering everything from pocket calculators to spacecraft. Welcome to the story of the microprocessor, a tale that begins not with silicon chips or integrated circuits, but with vacuum tubes, transistors, and the visionary engineers who dared to imagine computers that could fit on a desktop. To understand where microprocessors came from, we must first understand what came before. In 1946, the Electronic Numerical Integrator and Computer, or ENIAC, represented the cutting edge of computational power. This 30-ton behemoth filled an entire room at the University of Pennsylvania, containing over 17,000 vacuum tubes. Each vacuum tube was essentially an electronic switch, capable of turning electrical current on or off. But they had serious limitations. They generated enormous amounts of heat, consumed massive amounts of power, and burned out frequently. ENIAC required a full-time maintenance crew just to replace failed tubes. The vacuum tube was both a breakthrough and a bottleneck. Yes, it could switch electronic signals faster than mechanical relays, but it was also fragile, power-hungry, and took up enormous space. Engineers knew that if computing was ever going to move beyond specialized military and academic applications, they needed something fundamentally different. The scale of these early computers was staggering. The Harvard Mark I, completed in 1944, was 51 feet long and 8 feet high. IBM's SCC, unveiled in 1948, contained 12,500 vacuum tubes and weighed 30 tons. These machines were not just computers, they were architectural monuments to human ambition and engineering prowess. But the limitations were becoming increasingly apparent. A typical vacuum tube lasted about 3,000 hours before failing. In a machine with thousands of tubes, this meant constant breakdowns. The heat generated was so intense that early computer centers required industrial-grade air conditioning systems. The power consumption was enormous. ENIAC drew 150 kilowatts, enough to power 150 homes. More fundamentally, there was a physical limit to how complex these machines could become. You could only fit so many vacuum tubes in a room, and you could only cool them so efficiently. Engineers began to realize that vacuum tube technology would never lead to truly practical, widespread computing. The answer would come from an unlikely source: the study of semiconductors, materials that conduct electricity better than insulators like rubber, but not as well as pure conductors like copper. For decades, semiconductors had been scientific curiosities with limited practical applications. That was about to change. At Bell Laboratories, a team led by William Shockley was investigating the properties of semiconductor materials, particularly germanium and silicon. Their goal wasn't to revolutionize computing. It was to find a better amplifier for telephone systems. The existing technology relied on bulky vacuum tube amplifiers that were expensive and unreliable for long-distance phone calls. Walter Bratton and John Bardeen, working under Shockley's direction, were experimenting with the electrical properties of germanium crystals. They discovered that by placing two gold contacts very close together on the surface of a germanium crystal, they could create a device that would amplify electrical signals, just like a vacuum tube, but solid, compact, and requiring far less power. On December 23, 1947, they successfully demonstrated the first working transistor. The device was crude. The gold contacts had to be positioned by hand under a microscope, and the whole apparatus was fragile and temperamental. But it worked. The transistor could amplify signals and act as a switch, just like a vacuum tube, but it was a fraction of the size and consumed far less power. Shockley, initially excluded from the breakthrough discovery, quickly developed his own improved version, the junction transistor, which would prove to be more practical for mass production. The three men would share the 1956 Nobel Prize in Physics for their invention. But in 1947, few people understood the revolutionary implications of this small device. Bell Labs initially saw the transistor primarily as an improvement for telephone equipment. The computer industry barely existed, and those early electronic brains seemed destined to remain expensive, specialized tools for universities and government agencies. It would take more than a decade for the transistor's true potential to be realized. The first transistorized computers appeared in the late 1950s, and they were revelatory. The IBM 7090, introduced in 1959, was built entirely with transistors. It was faster, more reliable, and consumed far less power than its vacuum tube predecessors. More importantly, it was smaller and could be manufactured more economically. Transistors had another crucial advantage. They could be miniaturized. While vacuum tubes had reached their practical size limits, transistors could theoretically be made smaller and smaller, as long as manufacturing techniques could keep pace. This opened up possibilities that seemed like science fiction to engineers of the 1950s, computers that could fit on a desk, or even be carried around. The transistor revolution accelerated throughout the early 1960s. Companies like Fairchild Semiconductor and Texas Instruments began mass-producing transistors for a growing electronics market. Transistor radios became the first consumer electronics to showcase this new technology, creating a cultural phenomenon and demonstrating that solid-state electronics could be both practical and profitable. But transistors alone were not enough to create the microprocessor. Even transistor-based computers of the early 1960s required thousands of individual components: transistors, resistors, capacitors, and diodes, all connected by hand-soldered wires. Assembly was labor-intensive and error-prone. The next breakthrough would come from a seemingly simple idea. What if you could manufacture not just individual transistors, but entire electronic circuits on a single piece of semiconductor material? The integrated circuit was invented almost simultaneously by two engineers working independently, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. Both men recognized that the future of electronics lay not in connecting separate components, but in building everything on a single semiconductor substrate. Kilby's approach, demonstrated in September 1958, used germanium and connected components with fine gold wires. Noyce's version, developed a few months later, used silicon and a planar process that would prove more suitable for mass production. The basic principle was revolutionary. Instead of making individual transistors and then connecting them with wires, you could create an entire circuit: transistors, resistors, and connections, all in one manufacturing process. The first integrated circuits were simple affairs, containing just a handful of components. But they demonstrated a fundamental principle that would drive the electronics industry for the next half-century: integration. By putting more and more functionality on a single piece of silicon, you could make electronics smaller, faster, more reliable, and eventually cheaper. The early integrated circuits of the 1960s were primarily used in specialized applications: military systems, space missions, and high-end computers, where the premium price could be justified by the performance advantages. NASA used integrated circuits extensively in the Apollo guidance computer, one of the first major applications that demonstrated their reliability and compactness. As manufacturing techniques improved, integrated circuits became more complex. Simple logic gates gave way to more sophisticated functions. By the mid-1960s, engineers were creating circuits with hundreds of components on a single chip. The stage was being set for the next great leap: putting an entire computer processor on a single piece of silicon. But this required more than just manufacturing capability. It required a fundamental reconceptualization of what a computer could be. The computers of the 1960s were still massive, expensive machines designed for batch processing and shared among many users. The idea that every person might eventually have their own personal computer seemed absurd to most industry experts. The vision of ubiquitous computing existed primarily in the minds of a few far-sighted engineers and researchers. At places like SRI International and Xerox PARC, researchers were imagining a future where computers would be interactive, personal tools rather than shared institutional resources. But turning this vision into reality would require a new kind of processor, one that was small enough, cheap enough, and simple enough to be manufactured in large quantities. The semiconductor industry of the late 1960s was poised for this breakthrough. Manufacturing techniques had advanced to the point where complex circuits were feasible. The market for electronic calculators was exploding, creating demand for specialized computing chips. Most importantly, a new generation of engineers who had grown up with transistors and integrated circuits was beginning to imagine possibilities that their predecessors could never have conceived. The stage was set for the invention of the microprocessor. All that was needed was the right combination of vision, technical skill, and market opportunity. That combination would come together in the unlikely form of a contract to design chips for a Japanese calculator company at a small semiconductor firm in Santa Clara, California, that was just beginning to make its mark on the technology world. That company was Intel, and they were about to change everything. The year was 1969, and Intel Corporation was barely a year old. Founded by Robert Noyce and Gordon Moore, two refugees from Fairchild Semiconductor, Intel was trying to establish itself in the competitive world of memory chips. They had ambitious plans, limited resources, and a small team of brilliant engineers working in a modest building in Mountain View, California. Then came an unexpected opportunity that would change the course of computing history. A Japanese company called Bizicom approached Intel with a proposal. They wanted Intel to design a set of custom chips for a new line of electronic calculators. It seemed like a straightforward contract job, exactly the kind of work that a startup semiconductor company needed to pay the bills. But the Bizicom project was more complex than anyone initially realized. The Japanese engineers had designed a calculator that would require 12 different custom chips, each performing specific functions. This was an expensive and complicated approach, typical of the specialized logic design philosophy of the era. Each application required its own unique set of chips, designed from scratch. Ted Hoff, a young engineer at Intel, looked at the Bizicom specifications and saw something different. Instead of designing 12 separate chips for one specific calculator, what if they could create a single, programmable chip that could be instructed to perform any calculation? The chip wouldn't be hardwired for calculator functions. Instead, it would read instructions from memory and execute them step by step. This was a radical idea. Until this point, electronic devices were designed with fixed functions. A calculator chip could only calculate. A clock chip could only keep time. But Hoff was proposing something unprecedented, a general-purpose computing engine that could be programmed to perform any task, limited only by the software you fed into it. The concept wasn't entirely new. Large computers had been programmable for decades, but putting a complete programmable processor on a single chip was considered impossible by most engineers. The complexity seemed overwhelming, and the manufacturing challenges appeared insurmountable. Hoff's vision required compressing the essential elements of a computer, arithmetic unit, control logic, and registers, onto a single piece of silicon smaller than a postage stamp. This meant rethinking everything about processor design, finding ways to accomplish complex operations with minimal circuitry. Intel management was initially skeptical. Robert Noyce and Gordon Moore understood the potential, but they also understood the risks. This was uncharted territory, and failure could be catastrophic for their young company. However, they decided to support Hoff's vision, assigning him additional resources and talented engineers to make it work. The key breakthrough came when Federico Fagin joined the Intel team in 1970. An Italian engineer who had previously worked on silicon gate technology at Fairchild, Fagin brought crucial expertise in chip design and manufacturing. He would become the lead designer and project manager for what would eventually become the Intel 4004. Fagin's approach was methodical and innovative. He realized that to fit a complete processor on a single chip, every transistor had to count. Traditional computer designs were full of redundancies and inefficiencies that were acceptable when you had unlimited space and power. But in a microprocessor, every gate, every connection, every logic path had to be optimized. The team decided on a 4-bit architecture, meaning the processor would handle data in 4-bit chunks. This was a compromise between functionality and feasibility. 4 bits weren't enough for complex calculations, but multiple 4-bit operations could be combined to handle larger numbers. More importantly, a 4-bit design required fewer transistors, making it possible to fit everything on a single chip with the manufacturing technology available in 1970. The development process was painstaking. Fagan worked 18-hour days, designing logic circuits by hand, checking and rechecking every connection. Computer-aided design tools didn't exist yet. Everything was done with pencil, paper, and extraordinary attention to detail. A single mistake in the layout could render the entire chip useless. The manufacturing process was equally challenging. Intel's fabrication facilities were designed for memory chips, which had regular, repeating patterns. The 4004, with its complex logic structures, required new manufacturing techniques and quality control procedures. Many of the early chips were defective, forcing the team to refine their processes repeatedly. Meanwhile, Busicom was growing impatient. They had contracted for 12 specialized chips and were instead getting one general-purpose processor that they didn't fully understand. The relationship became strained as Intel focused on perfecting their revolutionary design rather than delivering exactly what Busicom had originally specified. In November 1971, after nearly 2 years of development, Intel finally announced the 4004 to the world. The marketing was modest, a small advertisement in electronic news with a headline, announcing a new era of integrated electronics. Few people outside the semiconductor industry paid attention. The significance of the moment was lost on most observers. The Intel 4004 contained 2,300 transistors on a chip measuring just 1/8 of an inch by 1/6 of an inch. It could execute 60,000 operations per second. Not fast by the standards of room-sized computers, but revolutionary for a device that could fit in the palm of your hand. The processor could address 4,096 4-bit words of memory and had 16 4-bit registers for temporary data storage. More important than the technical specifications was the conceptual breakthrough. The 4004 proved that a complete, programmable computer processor could exist on a single chip. This opened up possibilities that had never existed before. Computers cheap enough for small businesses, calculators powerful enough for complex mathematics, and eventually, personal computers for individual use. But the 4004 also had significant limitations. Its 4-bit architecture made it unsuitable for anything beyond basic calculations. The instruction set was minimal, and programming it required specialized knowledge that few people possessed. Intel recognized that they had created something important, but they also knew that this was just the beginning. The success of the 4004 led Intel to develop more powerful successors. The 8008, introduced in 1972, was an 8-bit processor that could handle more complex operations and address more memory. Unlike the 4004, which was designed specifically for calculators, the 8008 was conceived as a general-purpose processor that could be used in a wide variety of applications. The 8008 project actually began before the 4004 was completed. Computer Terminal Corporation had approached Intel about designing a processor for intelligent computer terminals. They wanted a chip that could handle text processing and simple computing tasks without requiring a connection to a mainframe computer. Ted Hoff and Stan Mazur led the 8008 development, building on the lessons learned from the 4004 project. The 8-bit architecture allowed for much more sophisticated operations, and the expanded instruction set made programming more practical. The 8008 could address 16,384 bytes of memory and had 7 8-bit registers, making it suitable for real computing applications. However, the 8008 still had significant limitations. It required multiple power supply voltages, complex external support circuits, and specialized packaging that made it expensive and difficult to use. These limitations prevented it from achieving widespread adoption, but it demonstrated that microprocessors could handle genuinely useful computing tasks. The real breakthrough came with the Intel 8080, introduced in 1974. This processor addressed virtually all of the limitations of its predecessors. It required only a single 5-volt power supply, had simplified external interfaces, and came in a standard 40-pin package that made it easy to integrate into electronic designs. The 8080 was faster, more capable, and more practical than any previous microprocessor. It could execute 290,000 operations per second and address 65,536 bytes of memory, enough for sophisticated software applications. The instruction set was comprehensive enough to support high-level programming languages, making it accessible to a much broader range of engineers and programmers. Federico Faggin led the 8080 development team, applying years of accumulated experience in microprocessor design. Every aspect of the chip was optimized for performance, manufacturability, and ease of use. The result was a processor that finally fulfilled the promise of the microprocessor concept. But Intel wasn't alone in recognizing the potential of microprocessors. Motorola, a major semiconductor company with strong expertise in communications electronics, was developing their own processor family. The Motorola 6800, introduced in 1974, offered an alternative approach to microprocessor design. The 6800 was designed by Chuck Peddle and his team as a complete system solution. Unlike Intel's processors, which required numerous support chips, the 6800 family included memory, input-output interfaces, and other essential components that could work together seamlessly. This system approach made it easier for engineers to build complete computer systems. The competition between Intel and Motorola drove rapid innovation in microprocessor design. Each company tried to outdo the other with more features, better performance, and lower costs. This competition was crucial for the development of the microprocessor market, ensuring that the technology would continue to evolve rapidly. Meanwhile, other companies were developing their own microprocessor designs. Zilog, founded by Federico Faggin after he left Intel, created the Z80 processor in 1976. The Z80 was backward compatible with the Intel 8080, but offered additional features and better performance. National Semiconductor developed the PACE processor, and Texas Instruments created the TMS 9900. Each of these processors had different strengths and was optimized for different applications. The diversity of approaches ensured that microprocessor technology would continue to advance rapidly, with each company pushing the boundaries of what was possible with single-chip processors. By 1975, the microprocessor revolution was well underway. These tiny chips were being used in electronic games, intelligent terminals, industrial controllers, and scientific instruments. Engineers around the world were discovering that microprocessors could replace complex hardwired logic with simple, programmable solutions. But perhaps the most significant impact was still to come. A few visionary engineers were beginning to imagine something that seemed impossible to most people: personal computers. Not shared terminals connected to distant mainframes, but complete, independent computers that individuals could own and use for their own purposes. The microprocessor had made this vision technically feasible for the first time in computing history. A complete computer could now fit on a desktop and be manufactured at reasonable cost. All that was needed was someone with the vision and determination to turn this possibility into reality. That someone was about to emerge from the unlikely world of hobbyist electronics, where engineers and enthusiasts were experimenting with microprocessors in their garages and basements, building the first primitive personal computers and dreaming of a future where everyone would have access to the power of computing. The age of the personal computer was about to begin, and the humble microprocessor, born from a contract to build calculator chips, would be the engine that powered this revolutionary transformation of human society. January 1975. A small company in Albuquerque, New Mexico, placed an advertisement on the cover of popular electronics magazine that would change the world. The headline read, "World's First Mini-Computer Kit to Rival Commercial Models." The product was called the Altair 8800, and it cost just $439 in kit form. For the first time in history, anyone with basic soldering skills and a few $100s could own a complete computer. The Altair 8800 was the brainchild of Ed Roberts, an engineer and entrepreneur who ran a small electronics company called MITS. Roberts had been watching the development of microprocessors with growing excitement. He realized that the Intel 8080, with its improved capabilities and reasonable cost, finally made personal computers economically feasible. But Roberts faced a fundamental challenge. How do you sell computers to people who don't understand what computers are for? In 1975, computers were still associated with large corporations, universities, and government agencies. The idea that individuals might want their own computers seemed absurd to most people. What would they do with them? Robert's genius was recognizing that there was a passionate community of electronics hobbyists who didn't need to understand practical applications. They wanted to build computers for the same reason that people build model airplanes or restore vintage cars, because it was fascinating, challenging, and fun. These hobbyists would be the early adopters, who would prove that personal computers were viable. The Altair 8800 was barely recognizable as a computer by today's standards. It had no keyboard, no monitor, and no storage system. Input was accomplished by flipping toggle switches on the front panel, and output was displayed as patterns of blinking lights. Programming required manually entering machine language instructions in binary code, a tedious and error-prone process that could take hours for even simple programs. Despite these limitations, the response was overwhelming. MITS expected to sell maybe 100 Altair kits in the first year. Instead, they received thousands of orders within weeks of the magazine's publication. The company was completely unprepared for this level of demand, and delivery delays stretched for months. The success of the Altair proved that there was real demand for personal computers, even in their most primitive form. More importantly, it catalyzed the formation of a community of computer enthusiasts who began meeting in groups to share ideas, trade software, and push the boundaries of what these small machines could do. The most famous of these groups was the Homebrew Computer Club, which began meeting in March 1975 in a garage in Menlo Park, California. The club attracted an eclectic mix of engineers, students, and curious amateurs who shared a common fascination with personal computing. Members would demonstrate their latest projects, share technical information, and engage in passionate discussions about the future of computing. It was at a Homebrew Computer Club meeting that Steve Wozniak first demonstrated the computer that would eventually become the Apple I. Wozniak, a brilliant but soft-spoken engineer at Hewlett-Packard, had been experimenting with microprocessor designs in his spare time. Unlike most hobbyist computers of the era, Wozniak's machine could display text on a television screen and accept input from a keyboard, revolutionary features that made it much more user-friendly than the Altair. But Wozniak wasn't interested in commercializing his design. He was perfectly content to share his ideas freely with the homebrew community and continue his hobby as a personal passion. It took the persuasive efforts of his friend Steve Jobs to convince him that their computer could be the foundation of a business. Jobs saw something that Wozniak missed. While Wozniak focused on the technical elegance of the design, Jobs understood that most people would never build computers from kits. They wanted complete, ready-to-use machines that worked right out of the box. This insight would prove to be crucial for the development of the personal computer industry. The Apple I, introduced in 1976, was sold as a fully assembled computer board for $666.66. Buyers still needed to add their own keyboard, monitor, and power supply, but the complex digital electronics were complete and tested. More importantly, Wozniak had designed the machine to be expandable and programmable, allowing users to customize it for their specific needs. The Apple I sold modestly. Only about 200 units were ever produced. But it demonstrated that there was a market for assembled personal computers, not just kits for hobbyists. This realization led Jobs and Wozniak to develop the Apple II, which would become one of the most successful computers in history. The Apple II, launched in April 1977, represented a fundamental shift in personal computer design philosophy. Instead of being aimed at technical enthusiasts, it was designed for ordinary consumers who wanted computers that were reliable, easy to use, and aesthetically pleasing. The Apple II came in a sleek plastic case, had color graphics capabilities, and included features like sound generation that made it suitable for games and entertainment. But the Apple II's most revolutionary feature was its open architecture. Unlike most computers of the era, which were closed systems that could only be modified by their manufacturers, the Apple II included expansion slots that allowed users and third-party companies to add new capabilities. This openness sparked an entire ecosystem of hardware and software companies that created products for the Apple II. The processor at the heart of the Apple II wasn't an Intel chip. Instead, Wozniak chose the MWES Technology 6502, a processor designed by Chuck Peddle after he left Motorola. The 6502 was similar in capability to the Intel 8080, but cost significantly less, a crucial factor for a company trying to build affordable personal computers. The story of the 6502 illustrates how competitive pressure was driving rapid innovation in microprocessor design. Peddle had been frustrated by Motorola's pricing strategy for the 6800 processor. He believed that microprocessors needed to be much cheaper to enable widespread adoption of personal computers. When Peddle left Motorola to join MOS Technology, he designed the 6502 to be backward compatible with the 6800, but manufacturable at much lower cost. The 6502 was introduced at the 1975 Wescon Trade Show with a price of just $25, compared to $179 for the Intel 8080 and $175 for the Motorola 6800. This dramatic price reduction made personal computers economically feasible for a much broader market. The success of the 6502 in the Apple II led to its adoption in many other important systems. Commodore used it in their PET computer, also introduced in 1977. Atari selected it for their video game consoles and home computers. The 6502 became the processor of choice for cost-sensitive applications, where Intel's higher-priced chips couldn't compete. Meanwhile, Intel was responding to this competitive pressure by developing more advanced processors. The 8086, introduced in 1978, was a 16-bit processor that offered significantly more performance than the earlier 8-bit designs. But the 8086 was expensive and complex, making it unsuitable for the emerging personal computer market. Recognizing this limitation, Intel developed a lower-cost version called the 8088. The 8088 had the same internal 16-bit architecture as the 8086, but used an 8-bit external bus, allowing it to work with cheaper support chips designed for 8-bit systems. This compromise made the 8088 more affordable while still offering improved performance. The processor wars of the late 1970s weren't just about technical specifications. They represented fundamentally different visions of what personal computers should be. Intel focused on performance and compatibility with existing business computer systems. MOS Technology and Motorola emphasized cost reduction and ease of use. Zilog, with their Z80 processor, tried to combine the best of both approaches. The Z80, introduced in 1976 by Federico Fagin's new company, was designed to be completely compatible with Intel's 8080, but with additional features and better performance. The Z80 included an enhanced instruction set, built-in memory refresh capabilities, and single-voltage operation that made it easier to use than the 8080. The Z80 became enormously popular in business computers and computer terminals. It was used in the TRS-80, one of the three major personal computers introduced in 1977, along with the Apple II and Commodore PET. The Z80's combination of performance, features, and reasonable cost made it an attractive alternative to Intel's processors. By 1979, the personal computer market was beginning to segment into distinct categories. At the low end were game-oriented computers like the Atari 400 and 800, which used the 6502 processor and emphasized graphics and sound capabilities. In the middle were general-purpose computers like the Apple II and TRS-80, which appealed to both hobbyists and small businesses. At the high end were professional systems like the S100 bus computers, favored by technical users. Each segment had different requirements, leading to continued innovation in microprocessor design. Game computers needed fast graphics processing and sound generation. Business computers required compatibility with existing software and reliable operation. Technical computers demanded maximum performance and expandability. The diversity of processor architectures during this period reflected the experimental nature of the personal computer industry. Nobody knew which approaches would ultimately succeed, so companies tried everything. Some processors emphasized simplicity and low cost. Others prioritized performance or special features. The market would eventually decide which strategies were viable. One of the most significant developments of this era was the emergence of software as a distinct industry. Early personal computers were sold primarily as hardware platforms that users programmed themselves. But as the market grew, it became clear that most people wanted ready-to-use software applications. The development of software applications created new requirements for microprocessors. Word processing programs needed enough memory addressing capability to handle large documents. Spreadsheet programs required fast arithmetic operations. Database applications demanded efficient data manipulation instructions. These software requirements began to influence processor design in ways that pure hardware considerations never could. VisiCalc, the first electronic spreadsheet program, was introduced for the Apple II in 1979 and became what many consider the first killer app for personal computers. Suddenly, people who had never considered buying a computer realized that VisiCalc could save them hours of manual calculations. The Apple II became essential business equipment, not just an interesting hobby. The success of VisiCalc demonstrated that software applications could drive hardware sales in ways that technical specifications never could. This realization began to change how computer companies thought about product development. Instead of focusing purely on hardware capabilities, they began to consider what software applications their systems needed to support. By the early 1980s, the personal computer revolution was in full swing. Dozens of companies were producing computers based on various microprocessor architectures. The Commodore 64, introduced in 1982, became the best-selling personal computer of all time, largely due to its low price and excellent graphics and sound capabilities, powered by the 6502 processor. But the fragmentation of the market was also creating problems. Software developers had to create separate versions of their programs for each type of computer. Users who wanted to upgrade to more powerful systems often had to abandon their existing software. The industry was crying out for standardization. That standardization would come from an unexpected source, IBM. The computer industry giant had watched the personal computer market develop with interest, but had been reluctant to enter what they saw as a toy market. By 1980, however, it was clear that personal computers were becoming serious business tools that threatened IBM's dominance in corporate computing. IBM's entry into the personal computer market would reshape the entire industry and establish Intel's x86 processor architecture as the dominant standard for personal computing. But that's a story for our next chapter, when we explore how the IBM PC changed everything and set the stage for the modern computer industry. The period from 1975 to 1985 had transformed microprocessors from laboratory curiosities into the foundation of a new industry. What started as a hobbyist movement had become a multi-billion-dollar market that was beginning to change how people worked, learned, and communicated. The personal computer revolution was no longer a revolution, it was the new reality. August 12, 1981. In a hotel ballroom in New York City, IBM held a press conference that would reshape the entire computer industry. The company that had dominated business computing for decades was finally entering the personal computer market with a machine they called simply the IBM personal computer. What nobody realized at the time was that this announcement would establish Intel's x86 processor architecture as the dominant standard for personal computing for the next 4 decades. IBM's decision to enter the personal computer market hadn't been easy. For years, the company's executives had dismissed personal computers as toys that would never threaten their profitable mainframe and mini-computer businesses. But by 1980, it was becoming clear that personal computers were moving into corporate environments and beginning to handle serious business applications. The catalyst was the success of VisiCalc and other business software running on Apple IIs. Corporate executives who had never considered personal computers were suddenly asking their IT departments why they couldn't have these powerful spreadsheet tools. IBM realized that if they didn't act quickly, companies like Apple and Commodore might establish themselves as serious competitors in the business computing market. But IBM faced a significant challenge. Their traditional approach to computer development was methodical and comprehensive, typically taking 4 to 6 years to bring a new system to market. In the fast-moving personal computer industry, that timeline would be fatal. By the time IBM finished developing a traditional computer, the market would have moved on to entirely different technologies. The solution came from an unlikely source within IBM, a small development group in Boca Raton, Florida, led by Don Estridge. Estridge proposed something revolutionary for IBM. Instead of developing everything in-house, they would build their personal computer using off-the-shelf components from other companies. This approach would allow them to develop a competitive system in just 1 year. The decision to use external components had profound implications for the computer industry. Instead of creating a proprietary system that only IBM could manufacture, they were essentially defining a new standard that other companies could copy. This openness was completely contrary to IBM's traditional business philosophy, but it was the only way to enter the personal computer market quickly. For the processor, IBM chose Intel's 8088. This decision wasn't based primarily on technical superiority. The 8088 was actually slower than some competing processors because of its 8-bit external bus. But Intel offered something that other processor companies couldn't: the promise of a continuing family of compatible processors that would provide an upgrade path for future systems. Gordon Moore and Andy Grove at Intel understood the strategic importance of the IBM design win. If IBM succeeded in establishing their architecture as the business standard, Intel would have a guaranteed market for millions of processors. They were willing to offer favorable pricing and technical support to ensure that the IBM PC would be successful. The IBM PC, Model 5150, was announced with a base price of $1,565 for a system with 16 kilobytes of memory and no disk drives. A fully configured system with 256 kilobytes of memory and 2 floppy disk drives cost $6,000. Expensive by hobby computer standards, but reasonable for business equipment. More important than the hardware specifications was what the IBM PC represented. For the first time, corporate purchasing departments had a personal computer from a vendor they knew and trusted. The phrase, "nobody gets fired for buying IBM," became a rallying cry for conservative IT managers who wanted to embrace personal computing without risking their careers. The initial success of the IBM PC exceeded everyone's expectations. IBM had projected sales of 250,000 units over 5 years. Instead, they sold that many in the first year alone. By 1983, the IBM PC was the best-selling personal computer in the business market, and other manufacturers were scrambling to create compatible systems. But IBM's open architecture strategy had an unintended consequence. Because they had used standard components and published detailed technical specifications, other companies could create computers that were functionally identical to the IBM PC. These clone computers could run the same software and use the same expansion cards, but they could be sold at lower prices because the manufacturers didn't have IBM's overhead costs. The first successful IBM PC compatible was produced by Compaq Computer Corporation, a startup founded by 3 former Texas Instruments engineers. The Compaq Portable, introduced in 1983, was a luggable computer that offered IBM PC compatibility in a package that could be carried from office to office. Despite weighing 28 pounds, the Compaq Portable was hugely successful because it allowed business users to take their computers and software with them. Compaq's success opened the floodgates for other clone manufacturers. Companies like Leading Edge, Tandy, and dozens of smaller manufacturers began producing IBM-compatible computers at increasingly competitive prices. This competition drove down costs and accelerated the adoption of personal computers in businesses of all sizes. Meanwhile, Intel was working on the next generation of x86 processors. The 80286, introduced in 1982, offered significant improvements over the 8088. It was faster, could address more memory, and included protection features that made it suitable for multi-user systems. But the 280SX's most important feature was its backward compatibility with 8088 software. Programs written for the IBM PC would run unchanged on 286 base systems. The 80286 was first used in the IBM PC/AT, announced in 1984. The AT advanced technology was significantly more powerful than the original PC and established many design standards that persisted for years. It used a 16-bit expansion bus that became known as the ISA. Industry Standard Architecture bus included a real-time clock and battery backup and could support up to 16 megabytes of memory. But the 286 also had significant limitations. Its memory management was complex and awkward, making it difficult for software developers to take full advantage of its capabilities. The processor could run in a protected mode that offered advanced features, but switching between real mode and protected mode was cumbersome and slow. These limitations became increasingly apparent as software applications grew more sophisticated. Lotus 123, introduced in 1983, quickly became the dominant spreadsheet program for business computers. But large spreadsheets could easily exceed the memory limitations of the 8088, and users demanded systems that could handle bigger and more complex applications. The solution came with Intel's 80386, introduced in 1985. The 386 was a true 32-bit processor that could address up to 4 gigabytes of memory and included sophisticated memory management capabilities. More importantly, it could run multiple programs simultaneously, each in its own protected memory space. The 386 represented a quantum leap in microprocessor capability. It was fast enough to run graphical user interfaces smoothly, powerful enough to support multitasking operating systems, and flexible enough to serve as the foundation for workstation-class computers. For the first time, a microprocessor could match the capabilities of traditional mini-computers at a fraction of the cost. But Intel faced a new challenge with the 386, competition from other companies that wanted to share in the lucrative x86 processor market. AMD, Advanced Micro Devices, had been producing second-source versions of Intel's earlier processors under license agreements, but they wanted to develop their own x86-compatible processors. The legal and technical battles that ensued would define the processor industry for the next 2 decades. AMD argued that they had the right to produce x86-compatible processors based on their earlier agreements with Intel. Intel countered that the 386 architecture was protected by patents and trade secrets that AMD couldn't legally use. While these legal battles raged, both companies continued to develop more advanced processors. Intel introduced the 80486 in 1989, which integrated a math coprocessor and cache memory onto the same chip as the main processor. This integration improved performance significantly and simplified computer design. The 486 was the first Intel processor to include sophisticated performance optimization features. The integrated cache memory reduced the number of times the processor had to access slow system memory, while the math coprocessor accelerated floating-point calculations used in scientific and graphics applications. AMD responded with their own 486 compatible processors that offered similar performance at lower prices. The competition between Intel and AMD drove rapid improvements in both performance and manufacturing efficiency, benefiting computer users with faster systems at reasonable costs. But perhaps the most significant development of this era wasn't technical. It was the emergence of Microsoft as the dominant software company for x86-based computers. MS-DOS, the operating system that IBM licensed for the PC, became the standard platform for business software development. Microsoft's success with MS-DOS gave them enormous influence over the direction of x86 processor development. Software requirements began to drive hardware design decisions in ways that had never happened before. When Microsoft decided to develop Windows, a graphical operating system that required significant memory and processing power, they worked closely with Intel to ensure that future processors would support Windows effectively. This collaboration between Microsoft and Intel became known as the Wintel Alliance, and it would dominate personal computing for the next 2 decades. Hardware manufacturers built computers around Intel processors and Microsoft operating systems, while software developers wrote applications for the Windows platform running on Intel processors. The Wintel Alliance was remarkably effective at driving technological progress. Each new version of Windows required more powerful hardware, encouraging users to upgrade their computers. Each new generation of Intel processors enabled more sophisticated software features, encouraging developers to create more demanding applications. This virtuous cycle accelerated the pace of innovation throughout the 1980s and 1990s. By the early 1990s, the x86 architecture had become the overwhelming standard for business computing. Apple continued to compete with their Macintosh computers based on Motorola 68000 processors, and various workstation companies offered high-end systems based on RISC processors. But the vast majority of business computers used Intel or Intel-compatible processors. The dominance of x86 processors had profound implications for the entire computer industry. Software developers could focus their efforts on a single architecture, reducing development costs and accelerating the introduction of new applications. Hardware manufacturers could achieve economies of scale by producing components for a large, standardized market. Users benefited from lower costs, better software availability, and easier system integration. But this standardization also had drawbacks. Innovation in processor architecture slowed, as the industry focused on evolutionary improvements to the x86 design rather than exploring radically different approaches. Companies that had developed alternative processor architectures found it increasingly difficult to compete against the entrenched Intel standard. The success of x86 processors also established Intel as the dominant force in microprocessor development. By the mid-1990s, Intel was spending billions of dollars annually on processor research and development, far more than any competitor could afford. This investment advantage allowed Intel to maintain technological leadership even as other companies tried to challenge their market position. The period from 1981 to 1995 had transformed the microprocessor from a component used in diverse computer architectures into the foundation of a standardized industry. The IBM PC's open architecture had democratized computer manufacturing, while the Wintel Alliance had created a stable platform for software development. But this stability came at a cost. By the mid-1990s, the personal computer industry was mature and predictable, dominated by a few large companies that competed primarily on price and incremental performance improvements. The wild experimentation and rapid innovation of the early personal computer era had given way to a more stable but less exciting industry. The stage was set for the next phase of microprocessor evolution, the performance wars of the late 1990s and early 2000s, when Intel and AMD would push x86 processors to unprecedented levels of performance, while new challenges emerged from mobile computing and the Internet revolution. March 22, 1993. Intel held a press conference in New York to announce their most important processor since the original 4004. The chip had a catchy name instead of just a number, Pentium. The marketing campaign was unprecedented in the semiconductor industry. Television commercials, print advertisements, and a distinctive 5-note audio logo that would become one of the most recognizable sounds in technology. The Pentium launch marked the beginning of what historians would later call the Performance Wars, a period of intense competition that would drive microprocessor performance to levels that seemed impossible just a few years earlier. Clock speeds would increase from 60 MHz to over 3 GHz. Transistor counts would grow from less than 4 million to over 100 million. And for the first time in computing history, processor performance would become a mainstream consumer concern. But the Pentium's introduction was about more than just technical specifications. Intel was making a fundamental shift in how they positioned microprocessors in the market. Instead of being invisible components that computer manufacturers selected, processors were becoming branded products that consumers would actively seek out. The phrase Intel Inside became as recognizable as Coca-Cola or McDonald's. The marketing strategy was born from necessity. Intel's previous processors had been identified by numbers: 286, 386, 486, but numbers couldn't be trademarked. Competitor companies, particularly AMD, were producing processors with confusingly similar names like AM386 and AM486. Intel needed a way to differentiate their products and build consumer loyalty. The Pentium processor itself represented a major architectural advance. It was Intel's first superscalar processor, meaning it could execute multiple instructions simultaneously. Where previous x86 processors executed instructions one at a time in sequence, the Pentium could begin working on a second instruction before the first one was completely finished. This parallelism significantly improved performance without requiring software changes. The Pentium also included separate instruction and data caches, advanced branch prediction, and a wider data bus that could transfer more information per clock cycle. These improvements combined to deliver performance that was typically 50 to 100% faster than the best 486 processors, even at similar clock speeds. But the Pentium's launch wasn't without controversy. In late 1994, a mathematics professor named Thomas Nicely discovered that certain floating-point calculations produced incorrect results. The bug affected only a tiny fraction of calculations, and only in very specific circumstances. But Intel's initial response was dismissive and defensive. The situation escalated when IBM announced they were halting shipments of Pentium-based computers until the problem was resolved. Intel's stock price plummeted, and the company faced a public relations disaster. Eventually, Intel agreed to replace any Pentium processor for any customer who requested it, at a cost of nearly $500 million. The Pentium bug incident taught Intel important lessons about consumer relations and quality control. More significantly, it demonstrated that microprocessors had become important enough to mainstream consumers that technical problems could become major news stories. The days when processors were invisible components, known only to engineers, were definitively over. While Intel was dealing with the Pentium controversy, their primary competitor AMD was developing processors that would challenge Intel's market dominance. The AMD K5, introduced in 1996, was designed to compete directly with Intel's Pentium but offered limited performance advantages. However, AMD was simultaneously working on a much more ambitious project, a completely new processor architecture that would become the K6. The K6 processor, launched in 1997, represented AMD's first serious challenge to Intel's technological leadership. Instead of simply copying Intel's designs, AMD had developed their own superscalar architecture that could execute x86 instructions more efficiently than Intel's processors. The K6 offered Pentium-level performance at significantly lower prices, forcing Intel to reduce their profit margins to remain competitive. But Intel wasn't standing still. The Pentium Pro, introduced in 1995, was designed primarily for server and workstation applications, where performance mattered more than cost. The Pentium Pro included sophisticated out-of-order execution capabilities that allowed it to rearrange instruction sequences for optimal performance. It also featured a large secondary cache memory integrated onto the same package as the processor. The Pentium Pro was followed by the Pentium II in 1997, which brought many of the Pro's advanced features to mainstream desktop computers. The Pentium II was notable for its distinctive slot-based packaging, which allowed Intel to include high-speed cache memory on a separate circuit board connected directly to the processor. This approach was more expensive than integrating everything on a single chip, but it allowed Intel to use faster cache memory than would have been possible with their manufacturing technology at the time. The late 1990s saw an unprecedented escalation in the processor performance race. Intel introduced the Pentium III in 1999 with advanced multimedia instructions and higher clock speeds. AMD responded with the Athlon processor, which was the first x86 compatible processor to achieve clock speeds over 1 GHz. The competition was driving performance improvements at a rate of 50 to 100% per year. This rapid performance growth was enabled by equally dramatic improvements in semiconductor manufacturing technology. Intel and other processor companies were investing billions of dollars in new fabrication facilities that could produce transistors at ever smaller dimensions. The transition from 0.5 micron manufacturing to 0.35 micron, then 0.25 micron, and eventually 0.18 micron processes allowed processors to become faster, smaller, and more efficient. But the focus on raw performance was creating new challenges. As processors became faster, they also became much more power-hungry and generated significantly more heat. Desktop computers required increasingly sophisticated cooling systems, and laptop computers struggled with battery life and thermal management issues. The power consumption problem became particularly acute with Intel's Pentium IV, introduced in 2000. Intel had redesigned their processor architecture to achieve very high clock speeds, eventually reaching over 3 GHz. But the Pentium IV's design prioritized clock speed over efficiency, resulting in processors that consumed much more power than their performance justified. AMD took a different approach with their Athlon 64 processor, introduced in 2003. Instead of pursuing maximum clock speeds, AMD focused on architectural efficiency and added 64-bit capabilities that could address much larger amounts of memory than previous x86 processors. The Athlon 64 often outperformed higher clock Pentium 4 processors while consuming less power. The introduction of 64-bit capabilities marked a significant milestone in x86 processor evolution. For the first time since the original 8086, the fundamental data width of x86 processors was expanding. This change enabled new applications that required access to large amounts of memory, such as scientific computing, digital content creation, and advanced database systems. But the performance wars weren't just about x86 processors. During this same period, alternative processor architectures were mounting serious challenges to Intel's dominance in high-performance computing applications. RISC-reduced instruction set computing processors from companies like Sun, IBM, and Silicon Graphics offered superior performance for specialized applications. The most significant RISC challenge came from a partnership between IBM, Motorola, and Apple called the PowerPC Alliance. The PowerPC processor was designed to combine the best features of RISC architecture with the economies of scale that came from multiple companies sharing development costs and manufacturing resources. Apple adopted PowerPC processors for their Macintosh computers starting in 1994, claiming significant performance advantages over x86-based PCs. The PowerPC architecture was indeed elegant and efficient, often delivering better performance per clock cycle than comparable x86 processors. But Intel's manufacturing advantages and software ecosystem proved difficult to overcome. The PowerPC Alliance faced fundamental challenges that ultimately limited its success. The three partner companies had different priorities and couldn't agree on a unified development strategy. Intel's massive investment in manufacturing technology gave them cost advantages that the PowerPC partners couldn't match. Most importantly, the vast majority of software applications were optimized for x86 processors, giving Intel-based systems significant practical advantages regardless of theoretical architectural superiority. During the same period, Sun Microsystems was promoting their Spark processor architecture for high-end workstations and servers. Spark processors offered excellent performance for scientific and engineering applications, and Sun's Solaris operating system was highly regarded in the technical computing community. But like PowerPC, Spark struggled against Intel's manufacturing scale and software ecosystem advantages. Silicon Graphics took yet another approach with their MIPS processor architecture, which powered high-end graphics workstations used for movie special effects and computer-aided design. MIPS processors were optimized for floating-point calculations and parallel processing, making them excellent for graphics and visualization applications. But as Intel processors became more powerful and graphics capabilities migrated to specialized graphics processors, the market for expensive MIPS workstations gradually eroded. The most successful challenge to x86 dominance came from an unexpected direction: embedded computing applications. ARM Holdings, a British company, had developed a processor architecture optimized for low power consumption rather than maximum performance. ARM processors were used primarily in mobile phones, handheld computers, and other battery-powered devices where energy efficiency was more important than raw computational power. During the 1990s, ARM processors seemed irrelevant to the mainstream computing market. They were much slower than x86 processors and couldn't run standard PC software. But ARM's focus on power efficiency would prove to be prescient as mobile computing became increasingly important in the following decade. The performance wars reached their peak in the early 2000s when Intel and AMD were locked in a fierce competition for clock speed supremacy. Marketing departments promoted each incremental increase in megahertz or gigahertz as a major breakthrough, and consumers were convinced that higher clock speeds automatically meant better performance. But this focus on clock speed was becoming problematic. As processors became faster, they also became much more difficult to design and manufacture. The physical laws governing electricity and heat transfer were imposing practical limits on how fast traditional processor designs could operate. Engineers were spending enormous amounts of time and money to achieve relatively small performance improvements. The limitations of the clock speed race became apparent when Intel encountered serious problems with their next-generation Pentium 4 design. The company had planned to reach clock speeds of 4 GHz and beyond, but power consumption and heat generation made such processors impractical for most applications. Intel was forced to cancel several high-speed Pentium 4 variants and reconsider their entire approach to processor design. AMD faced similar challenges with their high-speed Athlon processors. While they continued to compete effectively with Intel on performance, both companies were reaching the practical limits of single-core processor designs. The industry needed a new approach that could continue to improve performance without the drawbacks of ever higher clock speeds. The solution was already being developed in research laboratories: multi-core processors that combined multiple processing units on a single chip. Instead of making individual processors faster, manufacturers could improve overall performance by allowing multiple processors to work together on the same problems. IBM had demonstrated the viability of multi-core designs with their Power 4 processor in 2001, but that chip was designed for expensive server applications. The challenge was to bring multi-core technology to mainstream desktop and laptop computers at reasonable cost and power consumption levels. By 2005, it was clear that the performance wars as they had been fought during the 1990s were coming to an end. Single-core processors had reached practical limits, and the industry was preparing for a fundamental shift toward multi-core designs. The focus would change from raw clock speed to parallel processing capabilities, energy efficiency, and specialized functions. The era of the performance wars had transformed the microprocessor from a specialized component into a consumer product that ordinary people cared about and understood. Clock speeds had become as familiar to computer buyers as horsepower ratings were to car buyers. But the easy performance gains from higher clock speeds were ending, and the industry would need to find new ways to continue the relentless march toward more powerful computing systems. The stage was set for the next revolution in microprocessor design: the transition to multi-core architectures and the emergence of mobile computing as a driving force for innovation. The performance wars had ended, but the quest for better, faster, and more efficient processors would continue in new and unexpected directions. May 26, 2005. At the Intel Developer Forum in San Francisco, company executives made an announcement that would fundamentally change the direction of the microprocessor industry. After decades of pursuing ever higher clock speeds, Intel was officially abandoning the race for maximum gigahertz. Instead, they were embracing a new philosophy: more cores, not more speed. The announcement came with the introduction of the Pentium D, Intel's first dual-core processor for desktop computers. On the surface, it seemed like a modest evolution: 2 processor cores on a single chip, each running at relatively conservative clock speeds. But this represented a seismic shift in thinking that would reshape not just processor design, but software development, computer architecture, and ultimately how we interact with digital devices. The transition to multi-core processors wasn't just a technical decision, it was an acknowledgement of physical reality. The laws of physics were imposing hard limits on how fast electrical signals could travel and how much heat could be dissipated from increasingly dense semiconductor circuits. Engineers had reached what they called the power wall, the point where making processors faster also made them impractically hot and power-hungry. The solution was elegant in its simplicity. Instead of making one processor core twice as fast, put 2 cores on the same chip. This approach could theoretically double performance while keeping power consumption and heat generation manageable. But there was a catch: software applications would need to be completely redesigned to take advantage of multiple cores working simultaneously. For decades, programmers had written software assuming that processors executed instructions, one after another, in a predictable sequence. Multi-core processors required a fundamentally different approach called parallel programming, where tasks were divided among multiple cores that could work on different parts of the same problem simultaneously. This transition was extraordinarily challenging for the software industry. Many existing applications saw little or no benefit from additional processor cores because they weren't designed to work in parallel. Programmers had to learn new techniques for managing multiple threads of execution, synchronizing data access between cores, and debugging programs that could behave differently each time they ran. Intel followed the Pentium D with the Core 2 series in 2006, which represented a much more sophisticated approach to multi-core design. Instead of simply putting two existing processor cores on the same chip, Intel designed the Core 2 from the ground up to optimize communication between cores and share resources efficiently. The Core 2 processors also marked Intel's return to emphasizing architectural efficiency over raw clock speed. The new design could deliver significantly better performance per clock cycle than the Pentium 4, even while running at lower frequencies. This approach reduced power consumption and heat generation while still providing substantial performance improvements. AMD responded with their own multi-core processors, including the Athlon X2 and later the Phenom series. AMD's approach was different from Intel's. They focused on integrating the memory controller directly onto the processor chip, which could reduce latency and improve performance in multi-core systems. But while Intel and AMD were fighting the multi-core wars in desktop and laptop computers, a much more significant revolution was beginning in mobile devices. The introduction of smartphones and tablets was creating an entirely new category of computing devices with radically different requirements from traditional PCs. Mobile devices needed processors that prioritized battery life over raw performance. They had to be small enough to fit in thin, lightweight form factors. They needed integrated graphics, communication capabilities, and specialized functions that traditional PC processors didn't provide. Most importantly, they had to be manufactured at costs that would allow consumer devices to be sold at reasonable prices. The dominant processor architecture for mobile devices wasn't x86, it was ARM. The British company ARM Holdings had spent the 1990s perfecting processor designs that emphasized energy efficiency rather than maximum performance. While Intel and AMD were racing to achieve higher clock speeds, ARM was optimizing their designs to accomplish more work with less energy. ARM's business model was also fundamentally different from Intel's. Instead of manufacturing processors themselves, ARM licensed their designs to other companies who would customize and manufacture chips for specific applications. This approach allowed dozens of companies to create ARM-based processors optimized for different types of mobile devices. The smartphone revolution began in earnest with the introduction of the Apple iPhone in 2007. The iPhone used an ARM-based processor designed by Apple and manufactured by Samsung. This processor, later known as the A4, was specifically optimized for the iPhone's touchscreen interface, graphics capabilities, and battery life requirements. The iPhone's success demonstrated that consumers would embrace computing devices that prioritized ease of use and battery life over raw computational performance. The phone's ARM processor was much slower than contemporary desktop processors, but it was perfectly adequate for web browsing, email, multimedia playback, and the simple applications that defined early smartphone computing. Google's Android operating system, introduced in 2008, further accelerated the adoption of ARM processors in mobile devices. Android was designed from the beginning to run on a wide variety of ARM-based processors from different manufacturers, creating a diverse ecosystem of smartphones and tablets with different capabilities and price points. The mobile revolution created unprecedented demand for ARM-based processors. Companies like Qualcomm, NVIDIA, Texas Instruments, and Samsung began developing increasingly sophisticated ARM processors that integrated not just CPU cores, but graphics processors, communication radios, and specialized accelerators for functions like image processing and machine learning. Meanwhile, the multi-core transition in traditional PCs was accelerating. Intel introduced quad-core processors with the Core 2 Quad series in 2007, followed by the first-generation Core i7 processors in 2008. These chips included not just multiple cores, but sophisticated features like hyperthreading that allowed each core to work on multiple tasks simultaneously. The Core i7 also introduced Intel's Turbo Boost technology, which automatically increased clock speeds when thermal and power conditions allowed. This feature represented a new approach to processor performance. Instead of running at a fixed speed, processors could dynamically adjust their performance based on the demands of the software they were running. AMD responded with their own innovations, including the first consumer processors with integrated graphics capabilities. AMD's APU, Accelerated Processing Unit, combined traditional CPU cores with graphics processors on the same chip, providing better graphics performance and energy efficiency for mainstream computing applications. But perhaps the most significant development of this period was the emergence of software applications that could effectively utilize multiple processor cores. Video encoding, 3D rendering, scientific computing, and gaming applications began to show dramatic performance improvements on multi-core systems. The transition was particularly dramatic in gaming, where graphics processors were becoming increasingly important for delivering high-quality visual experiences. Companies like NVIDIA and AMD were developing graphics cards with hundreds or even thousands of processing cores optimized for the parallel calculations required for 3D graphics rendering. The integration of powerful graphics capabilities into computing devices was enabling new categories of applications that would have been impossible with earlier technology. Photo and video editing, computer-aided design, and scientific visualization applications could now run on desktop computers that cost a fraction of the specialized workstations that had previously been required. By 2010, the multi-core transition in desktop and laptop computers was largely complete. Most new computers included at least 2 processor cores, and high-end systems offered 4, 6, or even 8 cores. Software developers had adapted their applications to take advantage of parallel processing, and consumers had come to expect smooth multitasking performance from their computers. The mobile revolution was also accelerating. Apple introduced the iPad tablet computer in 2010, powered by their A4 processor and demonstrating that ARM-based devices could deliver compelling computing experiences for mainstream consumers. The iPad's success sparked a new category of tablet devices from numerous manufacturers, all powered by increasingly sophisticated ARM processors. The performance of ARM processors was improving rapidly. Apple's A5 processor, introduced in 2011, included dual cores and significantly improved graphics capabilities. Qualcomm Snapdragon processors were enabling Android devices with high-resolution displays, advanced cameras, and desktop-like web browsing performance. But the most significant trend was the convergence of computing capabilities across different device categories. Smartphones were becoming powerful enough to handle tasks that had previously required desktop computers. Tablets were offering laptop-like productivity capabilities, and traditional PCs were incorporating features like touchscreens and always-on connectivity that had originated in mobile devices. Intel recognized the threat that ARM processors posed to their long-term dominance and launched several initiatives to bring x86 processors into mobile devices. The Atom processor family, introduced in 2008, was designed specifically for low-power applications like netbooks and tablets. However, Intel faced significant challenges in the mobile market. Their x86 processors, despite continuous optimization, still consumed more power than comparable ARM designs. More importantly, the software ecosystem for mobile devices was built around ARM processors, and developers had little incentive to optimize their applications for x86-based phones and tablets. The period from 2010 to 2015 saw an explosion of innovation in mobile processor design. ARM introduced new processor architectures with better performance and energy efficiency. Companies like Qualcomm and Apple were pushing the boundaries of what was possible in smartphone and tablet processors. Apple's A7 processor, introduced in 2013 with the iPhone 5S, was the first 64-bit ARM processor used in a consumer device. This advancement brought desktop-class memory addressing capabilities to mobile devices and demonstrated that ARM processors could match or exceed the capabilities of x86 processors for many applications. The competition between different processor architectures was driving rapid innovation across the entire industry. Desktop processors were incorporating features developed for mobile devices, such as improved power management and integrated graphics. Mobile processors were adding capabilities previously found only in desktop systems, such as advanced encryption and virtualization support. By 2015, the microprocessor industry had been completely transformed from the single-core, high-frequency designs of the early 2000s. Multi-core processors were standard in all categories of computing devices. ARM processors had established themselves as the dominant architecture for mobile computing, and the boundaries between different types of computing devices were blurring as processor capabilities converged. The next challenge facing the industry was how to continue improving performance as manufacturing technology approached fundamental physical limits. Traditional approaches to increasing transistor density and reducing power consumption were becoming increasingly expensive and difficult to implement. The solution would require new approaches to processor design, including specialized accelerators for specific types of calculations, new materials and manufacturing processes, and innovative architectures that could continue to improve performance even as traditional scaling methods reached their limits. The industry was entering a new era where raw computational power would be less important than intelligent, efficient designs optimized for specific applications and use cases. November 10, 2020. In a virtual presentation broadcast from Apple's headquarters in Cupertino, CEO Tim Cook made an announcement that sent shockwaves through the technology industry. Apple was transitioning their entire Mac computer lineup from Intel x86 processors to their own custom-designed ARM-based chips, starting with the M1 processor. This wasn't just a processor upgrade. It was the end of a 15-year partnership and a direct challenge to Intel's decades-long dominance in personal computing. The M1 represented something unprecedented in computing history, a processor originally designed for smartphones that was powerful enough to run desktop and laptop computers. Early benchmarks showed that Apple's ARM-based chip could match or exceed the performance of Intel's best laptop processors while consuming a fraction of the power. The impossible had become reality. Mobile processor architecture was not just competing with desktop processors, it was winning. But the M1's success didn't happen overnight. It was the culmination of more than a decade of innovation in mobile processor design, combined with Apple's unique position as both a hardware manufacturer and software developer. The story of how we reached this point begins in 2015, when the microprocessor industry was grappling with the end of traditional scaling methods that had driven performance improvements for decades. Moore's Law, the observation that transistor density doubles approximately every 2 years, was facing serious challenges. Manufacturing processes were approaching atomic scales where traditional silicon-based semiconductors encountered fundamental physical limitations. Each new generation of processor manufacturing was becoming exponentially more expensive, and the performance benefits were diminishing. Intel, which had been the undisputed leader in manufacturing technology, began to encounter serious problems with their transition to smaller transistor sizes. Their 10-nanometer manufacturing process, which should have been ready by 2015, was delayed repeatedly due to technical difficulties. Meanwhile, competitors like TSMC, Taiwan Semiconductor Manufacturing Company, and Samsung were successfully implementing advanced manufacturing processes and gaining market share. The manufacturing challenges coincided with a fundamental shift in computing demands. Traditional processors had been optimized for general-purpose computing, where a single processor core could handle any type of calculation. But emerging applications like artificial intelligence, cryptocurrency mining, and high-resolution graphics rendering required massive amounts of parallel processing that traditional processors couldn't deliver efficiently. The solution was specialization. Instead of trying to make general-purpose processors faster, companies began developing specialized processors optimized for specific types of calculations. Graphics processors evolved into massively parallel computing engines suitable for machine learning applications. Dedicated AI accelerators were designed specifically for neural network calculations. Cryptocurrency miners used custom processors optimized for specific hashing algorithms. This trend toward specialization was most visible in the development of artificial intelligence applications. Machine learning algorithms required enormous amounts of matrix multiplication and other mathematical operations that could be performed much more efficiently on specialized hardware than on traditional processors. NVIDIA, originally a graphics processor company, found themselves at the center of the AI revolution. Their graphics cards, designed for 3D rendering in video games, turned out to be excellent platforms for training neural networks and other machine learning algorithms. The company's CUDA programming platform allowed developers to use graphics processors for general-purpose computing, opening up new possibilities for parallel processing applications. The rise of AI computing created entirely new categories of processor designs. Google developed their tensor processing units, TPUs, specifically for machine learning workloads. These specialized chips could perform certain AI calculations much more efficiently than traditional processors, enabling applications like real-time language translation and image recognition that would have been impossible with conventional hardware. Meanwhile, the smartphone industry continued to drive innovation in mobile processor design. By 2015, flagship smartphones were equipped with processors that rivaled laptop computers in many performance metrics. Apple's A-series processors, Qualcomm's Snapdragon chips, and Samsung's Exynos processors were incorporating advanced features like multiple processor cores, sophisticated graphics capabilities, and dedicated signal processors for camera and audio functions. The key to mobile processor success was integration. Instead of using separate chips for different functions, mobile processors combined everything onto a single piece of silicon. A typical smartphone processor included traditional CPU cores, graphics processors, image signal processors, communication radios, security processors, and specialized accelerators for machine learning and other tasks. This system-on-chip approach offered significant advantages in terms of power efficiency, cost, and physical size, but it also required a fundamentally different approach to processor design. Engineers had to optimize not just individual components, but the entire system working together efficiently. Apple's success with their A-series processors gave them confidence to attempt something that had never been done before, using mobile processor architecture as the foundation for desktop and laptop computers. The transition began with the development of the A12X processor for the iPad Pro in 2018, which demonstrated that ARM-based processors could deliver laptop-level performance. The breakthrough came with the M1 processor in 2020. Apple's chip included 8 CPU cores, an 8-core graphics processor, a 16-core neural engine for AI calculations, and numerous specialized processors for specific tasks. More importantly, it was manufactured using the most advanced semiconductor process available, giving it significant advantages in both performance and power efficiency. The M1 success forced the entire industry to reconsider long-held assumptions about processor architecture. Intel's x86 processors, which had dominated personal computing for 4 decades, suddenly looked dated and inefficient compared to Apple's ARM-based designs. Other companies began developing their own custom processors based on ARM architecture, including Amazon for their cloud computing services and Google for their data centers. But Intel wasn't standing still. The company launched an ambitious effort to regain technological leadership, investing billions of dollars in new manufacturing facilities and developing new processor architectures. The company's CEO, Pat Gelsinger, announced plans to become a major contract manufacturer for other companies' chip designs, competing directly with TSMC and Samsung. AMD also continued to innovate with their x86 processors. Their Ryzen series, based on the Zen architecture, offered competitive performance with Intel's processors, while often providing better value for consumers. AMD's success demonstrated that the x86 architecture still had room for improvement, even as ARM processors were gaining momentum. The competition between different processor architectures was driving innovation across the entire industry. Intel developed new manufacturing processes and architectural improvements. AMD focused on multi-core performance and energy efficiency. ARM-based processors continued to improve in both performance and capabilities. Meanwhile, the boundaries between different types of processors were continuing to blur. Traditional CPUs were incorporating AI accelerators and advanced graphics capabilities. Graphics processors were adding features that made them more suitable for general-purpose computing. Specialized AI processors were becoming more flexible and programmable. The rise of cloud computing added another dimension to processor development. Companies like Amazon, Google, and Microsoft were designing custom processors specifically for their data centers, optimized for the specific workloads they needed to handle. These processors often emphasized efficiency and cost-effectiveness over raw performance, leading to different design priorities than consumer processors. Edge computing, where processing is performed close to where data is generated rather than in distant data centers, created demand for processors that could deliver high performance while operating in challenging environments with limited power and cooling. This led to the development of specialized processors for applications like autonomous vehicles, industrial automation, and Internet of Things devices. The automotive industry became a major driver of processor innovation as vehicles incorporated more advanced electronic systems. Self-driving cars required enormous amounts of processing power for real-time analysis of sensor data, while electric vehicles needed sophisticated processors for battery management and motor control. Cryptocurrencies and blockchain applications created demand for processors optimized for specific types of cryptographic calculations. Bitcoin mining drove the development of specialized ASIC, application-specific integrated circuit, processors that could perform SHA-256 hashing much more efficiently than general-purpose processors. As we moved into the 2020s, the microprocessor industry faced several major challenges. The end of traditional Moore's law scaling meant that performance improvements would have to come from architectural innovations rather than simply making transistors smaller. The increasing complexity of modern processors made them extremely expensive to design and manufacture, limiting the number of companies that could compete at the highest levels. Environmental concerns were also becoming increasingly important. The massive energy consumption of data centers and cryptocurrency mining operations was contributing to climate change, creating pressure for more energy-efficient processor designs. The semiconductor industry was investing heavily in new materials and manufacturing processes that could reduce energy consumption while maintaining performance. The COVID-19 pandemic highlighted the critical importance of semiconductor manufacturing and created supply chain disruptions that affected everything from automobiles to consumer electronics. Governments around the world began investing heavily in domestic semiconductor manufacturing capabilities, recognizing that processor technology was too important to national security and economic competitiveness to be left entirely to market forces. Emerging technologies like quantum computing represented potential paradigm shifts that could eventually replace traditional semiconductor processors for certain types of calculations. While quantum computers were still experimental and limited to specialized applications, they demonstrated the potential for fundamentally different approaches to information processing. Neuromorphic processors, designed to mimic the structure and function of biological neural networks, offered another potential path for future computing systems. These processors could potentially offer dramatic improvements in energy efficiency for AI applications, though the technology was still in early development stages. As we look toward the future, several trends seem likely to shape the evolution of microprocessors. The continued growth of AI applications will drive demand for specialized AI accelerators and more efficient neural network processing capabilities. The expansion of 5G and 6G wireless networks will require processors with integrated communication capabilities and real-time processing performance. The Internet of Things will create demand for extremely low-power processors that can operate for years on battery power while still providing sophisticated computing capabilities. Autonomous vehicles will need processors that can make split-second decisions based on massive amounts of sensor data while meeting stringent safety and reliability requirements. Advanced manufacturing techniques, including new materials like gallium arsenide and indium gallium arsenide, could enable processors that are faster and more efficient than traditional silicon-based designs. Three-dimensional chip architectures could allow much higher transistor densities and better interconnections between different processor components. The microprocessor industry in 2025 looks radically different from the industry of 2015. What was once dominated by a few large companies producing general-purpose processors has evolved into a diverse ecosystem of specialized processors designed for specific applications. The competition between different architectures and approaches is driving innovation at an unprecedented pace. But perhaps the most significant change is that processors have become truly ubiquitous. They're not just in computers and smartphones anymore. They're in cars, appliances, medical devices, industrial equipment, and countless other applications that are transforming how we live and work. The humble microprocessor, which began as a way to build better calculators, has become the foundation of the modern digital world. In a small laboratory at Bell Labs in 1947, 3 scientists changed the world by creating a device smaller than a thumbtack. Today, more than 75 years later, we live in a civilization that would be unrecognizable to those pioneers. The microprocessor, the descendant of their transistor, has become the invisible force that powers virtually every aspect of modern life. To understand the true impact of the microprocessor, consider this. Right now, as you listen to these words, you are surrounded by dozens, perhaps hundreds, of these tiny computing engines. They're in your smartphone, your car, your television, your refrigerator, your thermostat, your watch, and countless other devices. The average American interacts with over 300 microprocessors every single day, most without ever realizing it. This ubiquity represents one of the most remarkable transformations in human history. In 1970, there were perhaps a few thousand computers in the entire world, each costing hundreds of thousands of dollars and requiring specialized facilities and trained operators. Today, a typical smartphone contains more computing power than all of those early computers combined, costs a few $100s, and fits in your pocket. The economic impact of the microprocessor is almost impossible to calculate, but economists estimate that the semiconductor industry directly generates over $500 billion in annual revenue, while enabling trillions of dollars in economic activity across virtually every sector of the global economy. From the internet to modern manufacturing, from medical devices to financial services, from entertainment to transportation, none of it would exist without the microprocessor. But the story of the microprocessor is more than just a tale of technological progress. It's a story about human ingenuity, vision, and the power of cumulative innovation. Each breakthrough built upon previous discoveries. Each generation of engineers stood on the shoulders of those who came before, and each advancement opened up possibilities that had never been imagined. The journey from the Intel 4004 to today's advanced processors represents one of the most sustained periods of technological improvement in human history. Moore's Law, the observation that computing power doubles roughly every 2 years, held true for over 5 decades, delivering improvements in performance, cost, and efficiency that seemed almost magical to outside observers. Consider the numbers. The Intel 4004 contained 2,300 transistors and operated at 740 kHz. Apple's M1 processor contains over 16 billion transistors and operates at over 3 GHz. That's nearly a 7 million-fold increase in transistor count and a 4,000-fold increase in operating frequency. If automobiles had improved at the same rate, a modern car would cost less than $1 and travel at millions of miles per hour. But raw performance numbers only tell part of the story. The true revolution has been in what these processors enable. The microprocessor didn't just make computers faster. It made entirely new categories of applications possible. Personal computers transformed how we work, communicate, and access information. Word processors replaced typewriters. Spreadsheet programs revolutionized financial analysis, and desktop publishing democratized the creation of professional quality documents. Email and the internet connected people across vast distances, while databases made it possible to store and search enormous amounts of information instantly. Mobile computing, enabled by increasingly powerful and efficient processors, has perhaps had an even greater impact. Smartphones have become the primary computing device for billions of people around the world, providing access to information, communication, entertainment, and services that would have seemed like science fiction just a few decades ago. The smartphone in your pocket can navigate anywhere in the world using GPS satellites, translate languages in real time, recognize faces in photographs, stream high-definition video from anywhere on Earth, and connect you instantly with anyone else on the planet. None of this would be possible without the sophisticated processors that can perform billions of calculations per second while running on battery power for an entire day. Artificial intelligence, one of the most significant technological developments of the 21st century, is fundamentally dependent on advanced microprocessors. Machine learning algorithms require enormous amounts of computational power to analyze data and identify patterns. The recent breakthroughs in AI, from image recognition to natural language processing to autonomous vehicles, were made possible by specialized processors that can perform the parallel calculations these systems require. The impact on scientific research has been equally profound. Modern scientific instruments generate vast amounts of data that must be processed and analyzed in real time. Climate models, genetic sequencing, particle physics experiments, and astronomical observations all depend on powerful processors to transform raw data into scientific understanding. Medical devices powered by microprocessors have saved countless lives and improved the quality of life for millions of people. Pacemakers regulate heart rhythms. Insulin pumps automatically manage diabetes. Cochlear implants restore hearing. And advanced imaging systems allow doctors to see inside the human body without invasive surgery. The manufacturing industry has been completely transformed by processor-controlled automation. Computer-controlled machine tools can produce parts with precision that would be impossible for human operators. Robots perform dangerous and repetitive tasks, while sophisticated control systems optimize everything from chemical processes to power generation. Even our entertainment has been revolutionized. Video games, which started as simple diversions, have evolved into sophisticated interactive experiences that rival movies in their production values and storytelling capabilities. Digital music, streaming video, and social media have fundamentally changed how we create, distribute, and consume entertainment content. The microprocessor has also democratized access to technology and information in ways that have profound social implications. A farmer in rural Africa can access the same information and use many of the same applications as a technology executive in Silicon Valley. Children in developing countries can receive educational content that would have been available only at elite institutions just a few decades ago. But this technological revolution has also created new challenges and concerns. The digital divide between those who have access to advanced technology and those who don't has become a significant source of inequality. Privacy and security concerns have emerged as personal information is stored and processed by countless computer systems. The environmental impact of our processor-dependent civilization is substantial. Manufacturing semiconductors requires enormous amounts of energy and exotic materials. Data centers that power the internet and cloud computing services consume significant amounts of electricity. Electronic waste from discarded devices creates disposal challenges. The concentration of advanced semiconductor manufacturing in just a few companies and countries has created strategic vulnerabilities and supply chain risks that have become apparent during recent global disruptions. The COVID-19 pandemic and geopolitical tensions have highlighted how dependent modern civilization has become on these tiny but critical components. Despite these challenges, the pace of innovation continues to accelerate. Artificial intelligence is enabling new capabilities that seemed impossible just a few years ago. Quantum computing promises to solve certain types of problems exponentially faster than traditional computers. New materials and manufacturing techniques are pushing the boundaries of what's possible with semiconductor technology. The next frontiers for microprocessor development are likely to be even more transformative than what we've seen so far. Brain-computer interfaces could allow direct communication between human minds and digital systems. Quantum processors could revolutionize cryptography, drug discovery, and scientific modeling. Neuromorphic processors that mimic the structure of biological brains could enable AI systems that are far more efficient and capable than current designs. But perhaps the most significant impact of the microprocessor has been on human potential itself. These tiny devices have amplified human intelligence and creativity in ways that would have seemed magical to previous generations. They've enabled us to solve problems, create art, explore space, cure diseases, and connect with each other in ways that were simply impossible before. The microprocessor has also changed how we think about problems and solutions. The ability to perform millions or billions of calculations quickly and cheaply has enabled new approaches to everything from weather forecasting to financial analysis to scientific research. Problems that were once intractable because of computational limitations can now be solved routinely. Looking forward, the challenges facing humanity, climate change, disease, poverty, energy sustainability, will likely require the continued advancement of microprocessor technology to solve. Climate models need more computational power to improve their accuracy and resolution. Medical research depends on processors to analyze genetic data and model biological systems. Renewable energy systems require sophisticated control processors to operate efficiently. The story of the microprocessor is ultimately a story about human ambition and ingenuity. It's about engineers and scientists who refused to accept limitations, who saw possibilities where others saw obstacles, and who had the persistence to turn visionary ideas into practical reality. From Ted Hoff's insight that a calculator could be a programmable computer, to Federico Fagin's meticulous circuit design, to Steve Jobs' vision of computers as personal tools, to today's engineers working on quantum processors and AI accelerators. Each generation has pushed the boundaries of what's possible. The microprocessor has proven that exponential technological improvement is achievable when human creativity is combined with sustained effort and investment. The progress we've seen over the past 50 years demonstrates that seemingly impossible goals can be reached through incremental advances and breakthrough innovations. As we stand at the beginning of the quantum computing era, the age of artificial intelligence, and the dawn of brain-computer interfaces, we can be confident that the next chapters of the microprocessor story will be even more remarkable than those that came before. The tiny piece of silicon that started as a way to build better calculators has become the foundation of human civilization in the 21st century. It has changed how we work, how we communicate, how we learn, how we entertain ourselves, and how we understand the world around us. But perhaps most importantly, the microprocessor has shown us that the impossible is merely the not yet achieved. The engineers who created the first transistors in 1947 could never have imagined smartphones, the internet, or artificial intelligence. Similarly, we can only begin to imagine what the next 50 years will bring as processors become even more powerful, more efficient, and more integrated into every aspect of human experience. The revolution that began in a Bell Labs laboratory with 3 scientists and a piece of germanium is far from over. In fact, it may just be getting started. The microprocessor has given us the tools to solve humanity's greatest challenges and to explore possibilities we haven't even begun to imagine. The story of the microprocessor is the story of human potential unleashed, and that story is still being written.